Now I introduce eligibility traces. We already introduced the n-step updates. Using the n-step updates, we can get the n-step return. The first term is the incident reward. From here to here, this is the cumulative reward. And we truncate at the t plus n. So we use this term as the approximation of the rest rewards from after this truncate point. Now we introduce these model parameters. We not directly update or estimate the state value function. Instead, we update the model parameters and to get the convergent state value function. To do so, we use TD lambda to calculate the return from a multiple episode, not just the one thought. And this includes two terms. The last term is TD1, that means the Monte Carlo method. The first term includes the rest of the episode. So this coefficient for the normalization purpose. If we use multiple episodes, we need to make sure the summation of its coefficient equals to 0 to 1 here. To estimate the state value function at the current state, in a forward view method, start from here, we make episodic sampling step by step until the terminal state. So to update the value function at the current state, we need to calculate the return at each state along the episode. And then now we take average of the return at each state along the trajectory and get this field, this state value function update. So how can we, if any way to not wait, or we complete all the returns at each state, and the way is a backward view. Backward view is another different method. It's the same thing. Purpose is to calculate the return or state value function return at the current state. But we want to calculate the return at the local state. At the same time, we update the model parameters. So we don't need to wait. We complete all the return calculation and then update the state value function at the current state. That means like at the local state, if we're far away from the current state, that means we got the return at this state. We have a very little contribution to the current state. If the state is closer to the current state, that means in time not far away. So the contribution, the return at this state have a larger contribution to the current state. Let's see how can we use the eligibility tracing method to update the model parameters. First, for example, this loss function, we use the gradient method. We calculate the derivative of this function with respect to the model parameter W. Not right now, we just let this function is a function of model parameters. So we calculate the derivative of this function, and you get this so-called Salmon gradient. So use this Salmon gradient, we can update the model parameters. To do so, we define the eligibility tracing vector Z. Z is only survive in one single episode. So at the beginning of each episode, we need to set Z equal to 0, and then we use this formulation to upgrade this eligibility trace vector. This is the Salmon gradient at the state ST. And then we use the one-step TD arrow this is the return, and here this is current. This is the actual state value function at the state st. So we defined this theta t. Use theta t and z, we can update the model parameters. Here, alpha is the learning rate. So let's see how can we update the model parameters step by step. First, for a new, for example, for a new episode, we select the initial state S, and we let this z equal 0. And then at the state S, we take action A, and we receive a reward R1. Here is R. And then move, agent move from the current state to next state. Because z equals 0, first z is equal to the Salmon gradient at the state S. And then we calculate the delta. And this is a temporal difference error. And then we update the W. That's the first step. And then I move to the next step, S prime. At S prime, this z is not a 0 anymore. So, but it's reduced by this factor, because this discount rate and this is the decay rate factor. Both of them less than 1. So this is less than 1, and then plus the Salmon gradient at this point, local state. And then we calculate, we update the model parameters here. This is the theta, this is delta, and this is z include 2 parts. One part is Salmon gradient. Then we should calculate this contribution to the local return. And the first part, because this is from the from the last Salmon gradient, but right now it's reduced. This number, that means we use this reduced or decay factor times this delta. That means the return at this state have a contribution to the current state is is controlled by this factor. So when I move to the next S prime state, and this we have this square. So this is the return at this state where less contribution than the S prime. When the state moves far away from the state S, so have a less contribution to this current state. That means we always look backward, and this is the local the time error is decay by a factor of this discount rate and this decay factor. So if the state far away from the current state, and it has a less contribution to the current state. However, when we calculate the contribution from each state, we don't need to wait, other contribution from other state. Once the model parameters reach to his convergence result distribution, then now we can get the state value function at the state S. For more details, please check with this reference. Thank you.